Hello, I know I'm behind schedule for doing this in Spring 24, but I hope this is still helpful for my students in future. Okay, this section will work on partial derivatives, and I think I don't need to do easy stuff, right? Like number 16. I do it anyway. Okay, let's see. Let's do number 16, number 20, should we do number 22? I think 24 is similar, huh? 24 and then 26 and 28. So while we basically just do partial derivative, which seems to be simple, but at the same time, we also review our calculus 1 and calculus 2. Okay, this time with a bit more complicated situation because it's multivariable, right? And therefore we do partial derivatives. Now let's see number 16. We have that fxy equals to x to the fourth y cubed plus 8x squared y. Then the partial respect to x will be, I think for this today, I will just write it as f subscript x. Okay, so that will be 4x cubed y cubed plus 16xy, while the partial with respect to y. So please don't misunderstand it as f times y. No, it's f subscript y. That's 3x to the fourth y squared plus 8x squared y. I think that's simple. It's polynomial after all. Okay, now and then number 20. Z sub x will be, the derivative of tangent is secant squared of xy times the derivative of xy respect to x, that's y. Z sub y will be x secant squared xy. Number 24. Of course, besides using subscript, we can also use partial derivative notation dou. Okay, so let me do that now. So dou w dou u is, you know what? That's e. Let me write down the function first because it's too small for me to see. That's w equals to e to the v over u plus p squared. So the partial of w respect to u will be, this e to the v is just the coefficient with in terms of u, right? So that's e to the v. Now the derivative of 1 over that will be 1 over u plus v squared to the squared with negative times the derivative of u, the partial of u plus v squared respect to u. So this will be negative e to the v over u plus v squared being squared times 1. While the partial respect to v will be, I think I need to do the quotient rule now, right? This will be u plus v squared being squared at the bottom. Okay, on the top, that will be e to the v times u plus v squared minus e to the v times 2v. I think that's simple enough, huh? So e to the v and then u plus v squared minus 2v over u plus v squared being squared. That's for number 24. Number 26, that u equals to sine of, that's compound function, sine r cosine theta. So the partial with respect to r will be cosine r cosine theta times the derivative, the partial of u cosine theta respect to r. Is that right? Okay, which will be just cosine theta times cosine of r cosine theta. And partial with respect to theta will be cosine r cosine theta times the derivative or the partial derivative of r cosine theta respect to theta. That will be negative r sine theta. Let me rewrite it. So this is negative r sine theta times cosine r cosine theta. Finally, number 28. That's a good question, by the way. fxy equals to x to the y. So when we do the partial with respect to x, the y is constant, right? That will be y x to the y minus 1. But when we do partial with respect to y, then x is the base. Is that right? So the derivative, the partial derivative of base to the y respect to y will be x to the y times the change of base ln x, right? Times the derivative of partial derivative of y respect to y, which is just 1. I wonder if you remember this. You can also think of that as the following. Let's say z equals to x to the y. We apply natural log both sides. And then we do the implicit differentiation with respect to y. Okay, so dou c dou y now equals to z natural log of x, which is x to the y natural log of x. I hope that explains. Okay, that's from Calc 2 though. Calc 2, we know that if we have z equals to e to the x, then the derivative respect to x will be just e to the x. Now, what happens if we have base a to the x? Then the derivative is itself times the change of base. Right? That's from Calc 2. Okay, let's go on. Oh, number 30. I think that's a good one. Number 30 seems to be interesting. Okay. The function capital F of alpha beta is the integral from alpha to beta of square root of t cubed plus 1 dt. So the partial of f respect to alpha will be, I wonder if you remember, this is actually fundamental theorem of calculus, right? That will be negative square root of alpha cubed plus 1. Long time no see, huh? And the partial of f respect to beta will be square root of beta cubed plus 1. Okay. What else? Maybe number 34. Number 34. Number 34. W equals to z e to the x y z. So the partial with respect to x will be c e to the x y z times the partial of x y z respect to x, right? That's the chain rule. Okay, if you can skip this chain rule thing, go ahead. Then this will be yz squared e to the x y z. The partial with respect to y will be c e to the xyz times xz, which will give us xc squared e to the xyz. And partial with respect to c, here I need to do product rule. C e to the xyz times the chain will be xy, which will becomes e to the xyz times 1 plus xyz. Okay. Number 38 seems to be quite interesting, huh? No, I don't want to. It's too hard. You do it. Number 36. Number 36. Well, number 38 is basically a lot of quotient rule, right? Okay. It's just like, because it is 4 variables, but you will see that z and t, for example, behave very similarly. X and y also behave similarly. U, number 36, u equals to x to the y over c, actually also similar to number 28 we have above, right? Okay, so the partial of u respect to x will be y over c minus 1. Okay, I'm sorry, not minus 1, times x to the y over c minus 1, right? Because x is the variable and y exponent y over c is the constant in this case, right? Okay, now how about partial of u with respect to y? Then we need to do change of base first, because then ax in this case will be the base, right? So the derivative will be itself times change of base times the derivative of partial derivative of y over z respect to y. Now that will give us itself times the change of base times 1 over z. Okay, and then the partial with respect to z will be the same. X here will becomes the base, x to the y over c times the change of base times the partial of y over c respect to z. That will be negative y over c squared. Let me make it nicer. So negative y over c squared x to the y over c natural log of x. Okay. Now let's say number 42. We need to find the partial of x function respect to x at 2, 3. So when I do the partial respect to x of xy, the derivative of arctangent is 1 over 1 plus x over y squared times the derivative of y over x respect to x. That will be negative y over x squared. Okay. You know what? Usually, of course, if we stop here, you're supposed to simplify, right? Okay, we're supposed to simplify. Let me simplify that a little bit. Then on the top, I get negative y. At the bottom, I will just multiply by x squared, right? So I get x squared plus y squared like that. Okay, not too hard, right? Okay, but what I meant is we need to plug in the numbers anyway at the end. So either you simplify the partial derivative, or you simplify after you plug in numbers. Either way, you have to simplify. But I think I prefer to do it this way. So this is negative 3 over 2 squared plus 3 squared. That's negative 3 over 13. Okay. Now, number 47 to 50, use implicit differentiation to find this. It's very nice of them to tell us to use implicit differentiation. Now, implicit differentiation here actually refers to two parts. Either you do regular implicit differentiation or you do the implicit differentiation theorem. Okay, now what I think I will do is I will do both of them. Okay, let's do the easy part first, number 48. Number 48, regular way. Okay, so we have x squared minus y squared plus c squared minus 2c equals to 4. We will do implicit differentiation with respect to x. So we get 2x minus 0 plus 2z dou c dou x minus 2 dou c dou x equals to 0. Okay, so I get dou c dou x times 2z minus 2 equals to negative 2x. I think we can cancel the 2. So dou c dou x is equal to negative x over z minus 1. Now that's the first method when we do partial respect to x. Now the second method, using implicit differentiation theorem, I define let function f of x, y, z equals to x squared minus y squared plus c squared minus 2c. Our textbook usually set it equals to 0, but actually not necessary. We can just set it into, as long as it is a constant. Okay, now and then the partial with respect to x will be 2x. The partial with respect to y, let me just do it at once, will be negative 2y. And partial with respect to z will be 2c minus 2. So dou c dou x is equal to negative partial with respect to z. I'm sorry, partial with respect to x over partial with respect to c. Okay, which is negative of 2x over 2z minus 1, and you see the minus 2, and you see the 2 cancels, right? And partial with respect to y, partial of z respect to y will be negative partial f respect to y over partial respect function f partial respect to z. That will be negative of negative 2y over 2c minus 2. That will give us positive y over c minus 1. Now you see that doing it by integration, implicit differentiation theorem seems to be shorter, okay? But of course, if you want to do it long way, that's not wrong, right? But get ready with making silly mistakes. When I say silly mistakes, it's a mistake that easily done by even somebody who is very mature mathematically. Okay, I'm sorry. I think I better say just including me. Okay, I think I'm pretty good with my math. I'm pretty good with my algebra, but I make miscomputation here and there. Okay, so implicit differentiation theorem, at least in this course, is being used for to help us with our computation. Okay, so we have 2c minus 2 times z sub y equals to 2y. So c sub y equals to y over c minus 1. I cancel the 2 at once. So you see that we get the same result, right? Okay, let's do one more, number 50. But as you can see, it's easier for us to do implicit differentiation theorem. I will just use implicit differentiation theorem. Number 50, augmentation, right? So yc plus x ln y equals to c squared. We define let capital F be a function of x, y, z, which is yc plus x natural log of y minus c squared, and then we set it into a constant, in this case 0. Now, partial with respect to x will be natural log of y. Partial with respect to y is c plus x over y. Partial with respect to z will be y minus 2z. So the partial of z respect to x, dou c dou x, or we can just say call that c sub x, is negative of partial of f respect to x over partial of f respect to z. That will be negative natural log of y over y minus 2z. Yeah, it's basically just using formulas, huh? Okay, this is partial with respect to y over partial respect to z equals to negative of z plus x over y divided by y minus 2z. Let me multiply the top and the bottom by y. So yc plus x over y squared minus 2yc. Let's go on further. Find all second partial derivative. Okay, so let's start with number 54 first then. At least see that as a warm-up. Okay, f of xy equals to sine squared of mx plus ny. So we first have partial respect to x and partial respect to y, right? Let's do them first. This is 2 sine of mx plus ny times the derivative of sine is cosine times the derivative of partial of that mx plus ny respect to x, that will be n, right? I think I can rewrite this as m times sine 2 times mx plus ny. Okay, now partial with respect to y is very similar to sine of mx plus ny cosine mx plus ny times n, which will give us n times sine 2 mx plus ny. You see, if you don't simplify this, then your next derivative will be a disaster, you know. Okay, let's see the partial of x respect to x, partial of f respect to x, and then respect to x. So basically I do this and do the derivative respect to x first. Okay, that will be the derivative of sine is cosine, so n times cosine of 2 mx plus ny times the derivative of this guy respect to x. That is simply 2m, huh? In other words, that is 2m squared cosine of 2 times mx plus ny. How about f sub xy, which is the partial respect to x being continued with respect to y? You will see that is 2mn cosine 2mx plus ny. Now you can try it yourself. Okay, now partial of f respect to y, that's the partial respect to y being continued by another derivative respect to y. That will be, you will see that's 2n squared cosine of 2mx plus ny. We know that is continuous, right? You will see that the mixed partial derivative respect to xy and respect to yx should be the same. Let's see. If I do the derivative of this respect to x, that will give me 2mn cosine of 2mx plus ny. And therefore, it shows the Clairaut's theorem. Okay. Let's see next, number 58. V equals to e to the x e to the y. Oh wow, somebody just want to make me work hard. So phi subscript x will be e to the x e to the y times the derivative of that exponent respect to x, so e to the y. Now, phi sub y will be, oh wow, itself, the derivative of this respect to y will be itself x e to the y. Huh. Okay. Now phi sub x will be, we do the derivative again respect to x here, so basically it becomes the same thing, huh? Becomes square, e to the x e to the y. And phi sub y, this one is nasty. It will be x e to the y squared e to the x e to the y. I do the derivative of this times this, that's what I get, plus this guy times the derivative of this respect to y. Okay, which will be e to the x e to the y times the derivative of this respect to y will be itself. I think I can do some factoring here. E to the x e to the y is the common factor. In fact, x e to the y also another common factor, right? X e to the y plus 1. Oh, that's nasty. Okay. Actually, we can put them together. This is x e to the x e to the y plus y times x e to the y plus 1. Mind you that what I had here is actually exponent. Okay, that's together as an exponent. While the one here is e to the x e to the y plus 2y, right? Okay, now the question is what happened to the partial with respect to x and then respect to y? As we expect, they are continuous, so it will be partial respect to y, respect to x. That will be the partial of this respect to y e to the x e y times x e to the y times e to the y plus this guy times the derivative of this respect to y, which is basically itself. Okay, let me factor them out. X e to the x e to the y plus y times x e to the y plus 1. I hope I don't make miscomputation though, seriously. Oh, let's make us think, huh? Okay, let's do a couple more. Find the indicated partial derivatives. Let's do number, I think number 64 is quite simple, huh? Right, it's just sign with some, let me just do it. Number 64, f of xy equals to sine of 2x plus 5y. So what is the partial with respect to y? So I do the innermost first. The partial with respect to y will be 5 cosine of 2x plus 5y. Then partial of respect to y, then respect to x, that will be negative 5 times 2 sine of 2x plus 5y, right? That is negative 10 sine of 2x plus 5y. You know what? Let me just do it here. Easier to see. So the next one, the partial respect to x, then respect to y, then respect to y. I'm sorry, y respect that y, and then x, and then y. So that will be negative 50 cosine of 2x plus 5y. Okay, number 66. G equals to e to the r sine st. We need g respect to r first. That will be itself, right? Respect to r, then s, that will be t e to the r cosine st. And then respect to r and then s and then t, that will be, I need to do product rule now, e to the r cosine st minus st e to the r sine st. I think I can just stop there, huh? Okay, the only common factor is e to the r. No fun. Okay, number 68. Let's see how painful this can be. We have this z here. Now, then I wonder if you understand this notation. This notation means you need to first do partial of z respect to w. And then you do partial of that dou c dou w respect to phi. Now, that is what dou squared c dou phi dou w mean. So the order is important, okay? And then finally, dou cube z respect to dou u dou phi dou w is actually the next partial derivative of dou squared c of dou phi dou w respect to dou u. That's what it means. Okay, now the thing is, we don't know the continuity of these functions. So instead of like second guessing, should I do it in this order or can I do it in any order? Let's just do it in this order. Okay, so when I do the partial with respect to w, this will be u over 2 square root of u phi minus w times negative 1, right? Okay, now then when we do the derivative with respect to v here, notice that this is actually negative u over 2 v minus w to the power of negative 1/2, right? So another partial with respect to v will result in positive u over 4 v minus w to the power of -3/2 times the derivative of v minus w respect to v, which is just 1. Now then, next, the derivative of that, the partial derivative of that respect to u. Oh, that one happens to be easy. Let me rewrite this nicer instead of using negative exponent, which is not really something we like. V minus w square root of v minus w. This guy here is just 1/4 of that. Okay, now number 72, we start thinking a bit. Okay, we have this ugly function here. Okay, and we need to find the partial with respect to x, and then respect to y, and then respect to z. Okay, the partial, assuming continuity, which we're supposed to check though, but with continuity, with clearance. Then the partial respect to x, y, z, instead of doing respect to x first, let's do respect to y and then c and then x. Now, what is the reason? Because we have x terms in both, right? Okay, when I do respect to y, you will see this guy disappear, right? Does it make sense? Okay. So this will be, we start with partial with respect to y. That will give us 0 plus 1/2 square root of 1 minus xy times negative x. Is it right? And then when we do partial with respect to z, that will be simply 0. So the partial with respect to y, c, x, that is 0. Don't you think it's nice? Okay, now you may, if let's see if we do it in the standard way. So the partial with respect to x will give us z over square root of 1 plus xz times 2, right? And then minus, when I do respect to, this is y over 2 square root of y minus xy. Now, when I do the partial with respect to y and x and then y, this guy disappear. But I have some issue here, right? I will have negative, I need to do quotient rule, huh? So 4, 1 minus xy, and then on the top I will get 2 square root of 1 minus xy minus y times 1 over, I don't know what is that. Okay, but you see that we don't have z anymore there, so the derivative of the partial derivative with respect to x and then y and then z will become 0 anyway. Okay, so so you see how helpful it's clearance, right? It allows us to do in different order, but of course we do assume continuity there. Okay, and that's for this one.